Okay, first of all, I would like to thank Shi and also Douglas to invite me to give a talk. And this talk actually based on the recent work date by 2013. So actually, this is a joint work with the Professor Jimpeng Chao, Professor Yupeng Wang in Physics Institute of the Physics Institute, Chinese Academy of Science, and also Professor Kang Jie-shi in Northwestern University, also with the Yao, the last two paper with the Yao in NTUQ. Actually, also I just have some other young guy like Peng Chen, probably so you know him, and he recently come back to the Xi'an. And so let's start. So actually, my talk divided by four part. The first part gives some introduction and also the motivation. The second part, I give the very typical integral quantum integral systems that has a no spin chain with periodic boundary condition. That is U1 symmetry system. And the first solution of this spin chain with periodic boundary condition given by Hansen Bethe almost 100 years ago. And second part, and the third part, I gave the Hansen spin chain with the very general integral boundary condition that one gave the challenge for many years until the 2013, also in the 13th. And most of the recently we will study about when the size, some kind of freedom of system may become very large. And that's very interesting in physics and how to calculate some physics quantities, even for the very general boundary condition which broke in the U1 symmetry. And finally, give some conclusion comments. So first section, first part, quantum integral system have many applications especially in string and gauge theory in the past 20 years. Very popular is ADS safety correspondence, and also have many applications in the supersymmetry, especially high supersymmetry Yang series. And also quantum integral system original from static mechanics, that is the Yin model. And another little bit general is the six vortex model and central. And also in constant matter physics, very popular is the supersymmetry TG model and Hubbard models. And also the quantum integral system driving the pure mathematics development, such as quantum group representation series and algebraic topology. Because the quantum integral system is already 100 years old, so there are many methods to solve the quantum integral system. And this moment and this talk are only interesting about T0. That means the only how to diagnose the one state. So the method, very popular method, the first one is called now is called the coordinate Bethe ansatz method. Is dated back the Hansen Bethe. And the second one is the who first found that the spectrum of the transfer matrix of the quantum integral system, especially for the with the U with associated with the SU2 case, that is the uniform relation, that's TQ. So that means all the eigenvalue can parameterize by the TQ relation. And a very powerful method that is developed in the end of the 17th, that the Bethe school, actually now it's called algebraic Bethe ansatz. That's very powerful for the most of the quantum integral system, which has the U1 symmetry, and because since the 1988, the work of the scanning, that means very general integral boundary condition can broken the U1 symmetry that quantum inverse scatter matrix or the Bethe groups, the method broken to solve this system, even this system is integral system. So this work actually until the 2013 with the Professor Yupeng Wang's school. I was a member of that school. We developed the off-diagonal method, Bethe ansatz method to solve, especially for the quantum integral system without U1 symmetry. That can solve this system by this method, and also this method seems to be very universal. That also can solve the model with the U1 symmetry. That can negate the answer from the quantum inverse scatter matrix, that's the algebraic Bethe ansatz, and also Bakes TQ relation, and also the Bethe ones. But for the U1 breaking system, only this method can solve this system. So the second part, I take a very typical example, that is the isomorphic chain. First, I can send this system actually is the one-dimension space, and it's on the lattice. Each lattice side, so we have the spin one half physics system, and the only interaction nearest neighbor interaction, and the coping is the like this one, this is the bulk interaction, and with the periodic boundary condition. And this system first solved by the Hyson Bethe in 1931. I think he recognized that this system have the many enough conserved charge, and also this abelian conserved charge ensure that this system can be in some quasi-particle picture. That system can eigenfunction can be linear expansion of the free system. That's because this abelian conserved charge guaranteeing that. And so this is actually since the work of the Bethe group. That means is the standard way to construct the conserved charge. That in this area we call it the transfer matrix, and they have the standard way to construct the conserved charge of that, and expand this transfer matrix with the with the variable u and the coefficient, and that is each coefficient is the operator action on the real hyperspace. That means is the 2 power n times 2 power n matrix. And the coefficient commute each other because the transform matrix commute each other with different spectral parameters. And our Hamiltonian actually can experience in terms of this coefficient for this particular Higgs-boson spin chain with the periodic boundary condition that can be like in this term, that is the inverse of the first one and times the second one. That means all the conserved charge of the HI is commuted with Hamiltonian because the Hamiltonian use the abelian commuted operators. So this proves the system is is integral systems. Actually, the constructor of the transform matrix can be built up from the R matrix. That is the local operator, some kind of, if you have the experience about integral system, that's some kind of R matrix is the L operator. And from local L operator, the build up the monodromy matrix. That is the 2 times 2 matrix, and each element is the operator action on the real hyperspace. So that is each capital A, B, C, D is the operator. That is the matrix of the 2n times 2n matrix. And because the build-up of the monodromy matrix starts from the R matrix, and this R matrix is not the arbitrary one, is the particular one, which satisfies the particular local Yang-Bass equation. If from the solution of the Yang-Bass equation and use this constructed monodromy matrix, and this even you can change the n no matter n how large, and input some particular fixed parameters set 1 to n, no matter n large or small, and they satisfy this kind of the relation that is ensured by the local Yang-Bass equation. And this equation also guaranteeing that the transform matrix, that is the A plus D operator commute to each other with different spectrum. That means expand the transform matrix as the parameter, the spectral parameter U, the coefficient commute to each other. So actually, here I use another way to solve this. Of course, with the periodic boundary, date back to the Hansen Bate give the solution, and also if they're very easy to use the algebraic ansatz to give the solution. Here I take another ways. That's because the build-up of these systems is a start from the R matrix. That's R matrix is this particular R matrix. This R matrix actually first found by the Wen-Li Yang. And this R matrix, so of course all the property of the transform matrix is includes in this R matrix. This R matrix satisfies this very common the condition, and based this condition, we can find out the transform matrix. They commute to each other, and also the product of this transform matrix with the spectral parameter choose particular one. One is U, another is shift by the eta. Eta is the parameter of the R matrix, and they satisfy this condition. And because the product they give descendants of the transfer matrix of the W, and also the T, because the product of the abelian operators. So the W also commute with the T, and the T commute to each other. And they commute to each other, use the common, they usually have the common eigenstate action on the common eigenstate. The eigenvalue of the transform matrix, they satisfy this condition, and this W is the eigenfunction of this operator W. And from construction of that, the lambda as the function of U is the polynomial with the degree of n, and the leading term coefficient is 2. That's and also W. You can use the fusion. You know that W actually is used Nazar matrix with the auxiliary space is the 3 times 3, 3 dimension, and from constructor that also W is the polynomial of the degree of n, and with the fixed leading term is 3, so that this particular polynomial can parameterize with his roots, and also W with his roots Wj, and the lambda with the roots of the Zj, and with the shift of the eta over 2. And also this A and D is the function, already know the function A and D is the function just with the theta I is the roots, and A is the shift of the D. So this is a fixed function. The zero of the D, this is a relation of polynomial. Unknown polynomial is the lambda and the W. And the D and A is a fixed function. And we know that the roots of the D is the theta I. So take the value of theta I, this equation actually become this term, because this is the theta J is the roots of D, and the W is the polynomial. So that means this condition, we have the n condition. And because lambda is the degree of the n with fixed leading term, the coefficient actually is the n. So there are n unknown coefficients. So we have the n condition, and this condition fixed this polynomial, and the solution of from the mathematics theorems, the solution of this equation actually is 2 power n. That means all the eigenvalue is a polynomial satisfies this condition, and the total solution is 2 power n. That means all the solution of this equation is the eigenvalue of transfer matrix. And of course, this 2 power n degree polynomial can parameterize in this form. In this form, where the QU is a particular polynomial with degree of m from 0 to n. And if you're familiar with the algebraic Bethe ansatz, you will know that transfer matrix, eigenvalue transfer matrix actually can be written out in this particular form. And this form is also called the Bakst relation. And this polynomial actually is not arbitrary one. That means lambda j should satisfy some condition. This condition actually is this one. This is actually is the Bethe ansatz solution. So actually, the solution of this one actually already gave by the algebraic ansatz. Of course, if you coordinate ansatz, you can also get this one. That means all the transfer matrix, the n-dimensional transfer matrix, that is the polynomial set, can write out this uniform relation, TQ relation, where the rows of the lambda J satisfy equation. So that means if you get the solution of this Bethe equation, then you get one solution, you get the polynomial, and input this polynomial into this TQ relation, you get the polynomial, which is the n-dimensional transform matrix. And from Bethe, that means from Bethe equation, you can get lambda, and from this equation, you can get the W. Actually, W and also can be written in this particular TQ relation. Now, the Bethe equation actually guarantees W and lambda is a polynomial. And of course, because this Bethe equation in this form is called the homogeneous Bethe equation, and this equation can you can start the n very large, the solution of this equation. That means that's Bethe equation you can analyze when the n very large for some particular state, some ground state. And in physics, they are very interesting in the ground state and exciting, non-energy exciting states. And because this equation very powerful to get this answer for particular state, this particular states. So that means you can use the Bethe equation to get to calculate the calculate the physical quantities, the interesting physical quantities, even for the older state, that for the finite temperature of T, for the zero temperature, only you can send a particular Bethe state that satisfies this equation, and for the thermodynamic limit for the finite temperature, you will involve all the solution of this Bethe equation, and this come to the TB8 thermodynamic Bethe. But in another way, you can also very naturally, you parameterize this 2 power n lambda u with its rows. And its rows actually, we know that the TQ parameterized for the U1 symmetry, you can choose another parameterize. But for the zero, the rows parameterize this polynomial. Actually, these two polynomial actually is unique. They have no freedom. But for this one, you can have the degree of m to change. So that means if you choose the rows of this one or this one, you can get another 2n equation. Let's say it's 2n equation. You can solve this equation, and you can get the rows of the lambda, the rows of that lambda, and also you can fix the lambda of u. And this equation is another way to get this lambda u. And for the U1 symmetry case, this one is very powerful to very large, and this way actually also very powerful to n very large. Actually, in the method in this talk, actually we use the parameterize of this rows of the lambda and the rows of the W to calculate the physical quantities even though n were large. So actually, for the second parameterize to solve this equation, we found out the pattern, the rows pattern of Zj and Wj have particular structure like the Bethe rows, because if you're familiar of the solution of Bethe equation, you know that for the particular state, the Bethe rows form some string, and also the rows of the lambda and the rows of W also form some string. It similar as the Bethe rows. Of course, you can use the solution of the Bethe. For U1 symmetry case, you can use the Bethe rows parameterized polynomial. Then you get the Zj and Wj and find out that have this structure. But U1 symmetry Brock systems, you can't use the parameterized backstick. You should add extra term. For that term, the solution of Bethe equation is very complicated, but the rows also form the same structure, the similar structure. So that first we started for a periodical case, and all the solution you can use the Bethe rows parameterized to get actually I think in the end of the 18th, Professor Paul Pierce, and also Baxter, and also some other people in Europe, they use this way to get the lambda, the potential function. And this actually is called the method of the inversion relation. And if you use the rows of the lambda u and the rows of w, you can easily get the same answer. But so just here I used another method to derive that the Bernoulli results, redirect the Bernoulli results. So lambda u for the ground state, we know the ground state, the lambda rows shift with the 8/2, they forms the pattern of the string with the imaginary part is the plus and minus 8, and the W is the string of the 3/2 eta. And the ground state lambda of u actually has its kind of the expansion. The first term is the periodical one. The second term is with the boundary, and the W also has this equation. And then very large, we found out the rows of the lambda and the rows of the W became dense on the rear line, the central part on the rear line. They form the density of the rows, both of the rows. And from this, the density, you can calculate the eigenvalue for the ground state. Actually, we get these results. And also, this is the same as use the different method is well known that results. And lambda j, you can find out. So the lambda j, lambda ground state energy can be written in this form. Of course, they already derived in the end of the 19th And from and also we know the roots of the W, and we use very large N, they form the density of the net one. You can usually calculate the for the ground state WG actually in this form, and use the T use the T relation of the product of the lambda. They should satisfy these two terms. And very important one, the second term, because second term for the U for you the real number actually is become the in this term, and very large. You can easily find out very large N. That means this term can vanish. Exportation very quickly to. So that's very large N. You can use the first term. That is the inversion relation in used people by Bax and also the Professor Paul, and plus some analytic property of lambda G. You can solve this inversion relation to get out that lambda of G actually is this form. So here we just gave the rederive that one. So what happened for the if the impose the integral bound condition that broken the U1 case, that means the spin chain become that one is the open one. The periodical one, and that means you can join the first one for the beginning and the end together. The open one, and with the boundary, we can impose the magnetic field on the boundary on the first side and the last side. And if the psi is 0, that means the two boundary magnetic field is parallel with each other. And if you can say non-zero, that means unpolarized. They have the angle between these two magnetic field, and because without vanish, actually the solution of this equation, the diagonalized this Hamiltonian until 2013. That's our first work on it. Before that, nobody know how to solve that one, get the correct answer. So this in the 1988, scanning already proved that this system is the integral system. You can construct the transfer matrix that is generation function of the order abelian conserved charge. In this case, you should need the 2K matrix. That's one is corresponding this boundary magnetic field, and the second one is correspond the second one, and this is the most general interaction for the azimuth spin chain with the unparalleled magnetic field. And also that, of course, you can use the same method for the periodical one. We found out that the Trachtenberg matrix actually they satisfy this condition, and this A and D is a fixed fixed function. It depends on the theta, that's the shift of the R matrix, and also the boundary parameters. And we know that the W and T commute each other if you add action on the Coleman eigenstate. you will find out the eigenvalues should solve my equation. And here lambda and w is the particular polynomial, but here is with the degree of the 2n plus 2. But because the special construction of the transform matrix and this lambda satisfy this condition, that's just roughly speaking, is with the shift of the 8/2 become the even function. Even function, that means even degree is the 2n plus 2, actually a no non-vanished and no coefficient is the n plus 2, is n plus 2. And you should actual two condition, that is these two condition you can fix out. Of course, you can parameterize this 2 over n polynomial in terms of the TQ, some kind of the TQ, but if cosine is not vanished, you should add extra term. This extra next one is the first two terms. So the people in this area, we call this with vanished this term, we call it homogeneous TQ, but have this term is inhomogeneous TQ. But for most general integral systems, it should be parameterize the eigenvalue of transformations in terms of inhomogeneous term only for some particular trace. For this case, it's say 0 case, you can parameterize in two terms. And because the U1 symmetry broken, so the symmetry, the Hamiltonian, you can easily find out that this both case, they have the rotation around three direction. That is the SO3 internal space, the continue rotation. But if the open these systems, that for the first magnetic field, impose the first magnetic field and one side, that means this system, the SO3 broken to U1, that's the rotation around Z direction. You can rotation around Z direction for the second magnetic field and make it in the XZ plane. That means you can parameterize the most general Hamiltonian in this case. So for the cosine is non-zero, that means the SO3 broken to the one part is SU1, and because cosine is non-zero, then this broken to no continue one. That means broken all the SO3 continuous symmetry. So that means the original M. So the Q here is the parameterize of the Q. If you remember, for the U1 symmetry case, that's this Q have degree of freedom from 0 to n. But for this case, it's fixed and n because they have no U1 symmetry. And of course, the Q should set is not arbitrary polynomial. They should satisfy this condition. And you get each solution of that one corresponding to one state and the corresponding to one eigenvalue of that one. But because they are non-vanished of this term, so that's very the structure of the solution of this equation is become very complex. If very large n, people can not easy to get the pattern of the solution. But if you use another parameter choice, like the periodic case, use the analysis of the polynomial. That means of the results of the z and the results of the w and the solution of this equation. You will find out that the most of the results of the z, they form the strings, except some string and with the only imaginary part. That means the center of the string is on the zero of the real line. Only this string, we call it boundary strings, depends on the parameter of the boundary magnetic field. And the change the magnetic field, they will change how large of these strings. And the most of the rows actually is focused on the two strings, and no change of that one. With this kind of structure, we can can get the ground state. Of course, this is for the ground state, the structure of the parameters. And they can write out in this form, and with very large N, you can have this kind of expression. That one, use the similar method, we can easily get the ground state integer can be written in this term. The ground state of another descendants transfer matrix can be eigenvalue can be expressed in this term, and also we can get the product of that one in this form. Actually, this form also means that and this term will be explosion decay when n very large. That means very large n, you can ignore this term, use some kind of generalize the inversion relation to plus some analytic property of the lambda. You can get the lambda. And of course, they can have this kind of the solution, only this kind of solution. In this talk, actually, the most important ones use this method to solve this one. This one is the new results, but the original one is for the U1 symmetry case, you can use another parameterized like the TQ parameterized to solve that. That TQ parameterized also relate the solution by the method of the algebraic Bethe ansatz. But it seems our method actually, here I only gave the example for the first and the second one. But actually, this method seems to be universal one. You can generalize to other algebra, and also we solve for the supersymmetry TJ model with the very general boundary magnetic field, and also the Harvard model. So we believe that this method is universal one for the Yang-Bast integral system. That means the transformation constructed from the Yang-Bast solution of Yang-Bast equation. That means the standard solution of Yang-Bast equation. So actually, I think here I stopped here, and thanks for your attention.
Okay. So thanks for Wen-Li's wonderful talk. So is there any particular questions for this speaker that you guys want to ask?
And I have a questions. I mean, for the cases about the open Heisenberg spin chain, we will have the different boundary condition that we add to different, magnetic field on the both side, and you have the figure to show I mean, only the boundary will affect by the magnetic field, I mean, in the original point, and other one is separate on the real axis, but only a boundary at the origin, it will separate on the imaginary axis. I want to ask, like, is that will be affected by the, I mean, if the magnetic field on both sides are parallel or unparallel, because you have the I mean the psi parameters on the equation 11, it will shows if the magnetic field are parallel or not.
Yes, this is the most general one. Very interesting question, and because the bulk is you can rotation around three direction. So that means you can use the rotation to make the first side magnetic field around the z direction without change of the bulk one, because the bulk one is the rotation around three direction. So the first, for the most general one, even they has six parameters. You can rotation, and for the first one is the z direction. Then the system is broken to the around the z direction without change of that one and without change of that one. But this in general, you have the three components. You can rotation around z direction to make the magnetic field in the xz plane. So they have only two components. This is the most general one. So all the magnetic field with unpolarized can be parameterized in this this Hamiltonian. If you consider xz case, this have the delta. Then original one is the only rotation around z direction. So you can write out in this form. You have the 5, 1. So you can rotation around z direction to make the first one in the xz plane without change of that one. But this one, actually, they have the three components. So for xz case, they have the 5 parameters, most general one. And if have the xyz, that means the three constants different. You have no rotation around any direction. And that means you have the 6 parameter corresponding to the magnetic field and 3 components in the first side and 3 components on the inside. So this actually is the most general one for the Heisenberg speech.
Okay, yeah. And I have another questions like after this slide, and I remember you said when the number of the spin chain goes to the infinity, one of the it's like the tangent terms will disappear. I mean, for the solution, you get, I mean, for the which have the tangent like in the final page, I think. I mean, is that
Yeah.
this pages. I mean, for you just mentioned for the when n goes to infinity, the I mean TANH, I don't know how to read that, will disappear. Will it affect the equation 17? I mean, will it still keep the same form for like when n goes to infinity for the thermodynamics limit situation?
Yes, this actually you can expand this one as the expansion of some so this term actually you can write out in this term, and of course this equation only become the equation here is the rare equation because if you have the coefficient of the n minus 1 over n plus some coefficient times 1 over n square or all of that one. But if the consider some isotopic behavior of the lambda you if you impose of this one, you can expansion of the exportation one, you will find that, and the first term is become this one. Of course, if the this term n very large, this actually becomes 0. That means the product of this two plus some kind of a fixed function that only determine the first term. Actually, this original were known for the periodical case, U1 case. That's in the end of the 19th. I think probably the first one is from Baxt solve this equation without this term. For the periodical case, only but for the boundary case, no one know they have this kind of structure. So for periodic case, that means this term is 0. For large n, you can only focus on the first term and plus some analytic property of lambda j. You will find out the solution of that unique solution of that one can be right in this. So it's the same. But of course, you can use the parameterize of the beta rows. Use this equation. You can also to get the same answer. But for the U1 brokerage, for the open case, for most general cosine non-zero, nobody knows that.
Okay, yeah, I see. Thank you. Thank you for the answers.
Okay. So I think, is there any more questions for the speaker? Okay, if no more questions, let's thank the speaker again for the wonderful talk.
Thank you.
Okay. So all right. So I think Yang, you may chair after this.
Yes. So for our next speaker, we welcome Dr. Xiao Wang from Cornell University to talk about non-equilibrium dynamics in an Ising chain with periodically driven transverse field. I think there are still 6 minutes until 2 p.m. So maybe we will start this talk in 6 minutes. Yep.
Okay, sure.
Hi. So, Dr. Wang, you may start whenever you're ready.
Sure. So can you see the screen? So it is sharing now, I guess. Let me play it.
Yep, yep,
So,
can see this.
okay, great. Okay, great. So I guess I'm already ready, so we can start now, maybe.